Hello guys, welcome to Surparts Online, and today we're going to have the tutorial for the data science, and we're going to have these linear functions. So mathematical functions are important to know as a data scientist because we want to make predictions and interpret them. So linear functions. In mathematics, a function is used to relate one variable to another variable. Suppose we consider the relationship between calorie bornage and average pulse. It is reasonable to assume that in general, the calorie bornage will change as the average pulse changes. We say that the calorie bornage depends upon the average pulse. Furthermore, it may be reasonable to assume that as the average pulse increases, so will the calorie bornage. Calorie bornage and average pulse are the two variables being considered. Because the calorie bornage depends upon the average pulse, we say that calorie bornage is the dependent variable and the average pulse is the independent variable. The relationship between a dependent and independent variable can often be expressed mathematically using a formula or a function. A linear function has one independent variable x and one dependent variable y and has the following form: y equals function of x equals ax plus b. This function is used to calculate for the dependent variable when we choose a value for the independent variable. Fx is the output, the dependent variable. X, the input, the independent variable. A is equal to slope. It is the coefficient of the independent variable. It gives the rate of change of the dependent variable. B, intercept, is the value of the dependent variable when x is 0. It is also the point where the diagonal line crosses the vertical axis. So we have linear function with one explanatory variable. A function with one explanatory variable means that we use one variable for prediction. Let us say we want to predict a calorie bornage using average pulse. We have the following formula. Fx is equal to 2x plus 80. Here, the numbers and variable means Fx, the output. The number is where we get the predicted value of calorie bornage. X, the input, which is the average pulse. 2, the slope, specifies how much calorie bornage increases if average pulse increases by 1. It tells us how steep the diagonal line is. 80 is equal to intercept, a fixed value. It is the value of the dependent variable when x is 0. Plotting a linear function. The term linearity means a straight line. So if you show a linear function graphically, the line will always be a straight line. The line will always be a straight line. The line can slope upwards, downwards, in some cases may be horizontal or vertical. Here is a graphical representation of the mathematical function above. So explanation of the graph. The horizontal axis is generally called x-axis. Here it represents the average pulse. The vertical axis is generally called the y-axis. Here it represents the calorie bornage. Calorie bornage is a function of average pulse because calorie bornage is assumed to be dependent on average pulse. In other words, we use average pulse to predict calorie bornage. The blue diagonal line represents the structure of the mathematical function that predicts calorie bornage. Let's click next. The Sports Watch dataset. Take a look at our health dataset. So as we remember, the duration, average pulse, max pulse, calorie bornage, hours work, and hours sleep, these are our variables. So putting this existing data in Python, we can use this particular program. So, import matplotlib.pyplot as PLT. Health data.plot x equals average polls, y calorie burnage, kind equals line. PLT ylim ymin equals 0. PLT.xlim xmin equals 0. PLT.show. So let's try it yourself in order to get our values. So we have two imports here. Import sys, import matplotlib, then matplot.lib use agg. So import pandas as pd, import matplotlib.pyplot as plt. So our health data, we read the value from our data CSV. This is our data CSV. So we read that using this particular code and with a header and a separator of comma. No? Then after that, we have this health data.plot x equals average polls, y calorie burnage, kind equals line. PLT.y limit, y min equals 0. PLT.xlim, x min equals 0. So this 0, guys, is this, no? So if you try to change this one to 10, let's try to change this to 10. And let's try to run. What will happen to our y? Okay, so what happens is it automatically 0 to 50 here, no? On this one. While if we're going to use 0 to 0, let's check if it's the same. 50, 20, no? They're just the same, no? They're just the same. But as you can see here, there are two zeros here. If I'm going to change this to, let's say, 2, let's try to change that to 2. And as you can see, there's only 1 0, no? How about if we change this to 1, guys? I don't see the difference, no? I could not see, guys. So you just copy the code in order to make like this one. So it started at 80, no? It started at 80 here, somewhere in 80. The line started at 80 because the smallest data here for our average polls, which is the second line, is 80. There you go. You can see there it says 80. So it starts at 80. We have 85. If we're going to change this to, let's say, 0, it run, the line would be at the 0, somewhere like that, 0. So let's give this back to 80, return this to 80, and run. And then we are going to go back to, okay, so that's the code, guys, to make, okay, so explanation, import the plot module of the matplotlib library, plot the data from the average polls against calorie burnage. So that's that one. And kind equals line tells us which type of plot we want. Here we want to have a straight line. PLT.ylim and PLT.xm tells us what value we want the axis to start on. Here we want axis to begin from 0. So it's 0. PLT.show shows us the output. PLT.show. So that's the output, guys, the graph. As you can see, there is a relationship between average polls and calorie burnage. Calorie burnage increases proportional with the average polls. It means that we can use average polls to predict calorie burnage. That's good, guys. Huh? Why is the line not fully drawn down to the y-axis? The reason is that we do not have the observations where average poles or calories are equal to 0. 80 is the first observation average poles, and 40 is the first observation of calorie bornage. So as you can see on the red line, guys, so that's the first data that we have. Look at the line. What happens to the calorie if average poles increases from 80 to 90? We can use the diagonal line to find the mathematical function to predict calorie bornage. As it turns out, if the average pulse is 80, the calorie borne age is 240. If the average pulse is 90, the calorie burn is 260. If the average pulse is 100, the calorie borne age is 280. So there is a pattern. So if the average pulse increases by 10, the calorie borne age increases by 20. So we could have the pattern. Okay, slope and intercept. So now we will explain how we found the slope and the intercept of our function. So fx equals 2x plus 80. The image below points to the slope, which indicates how steep the line is, and the intercept, which is the value of y when x equals 0. The point where the diagonal line crosses the vertical axis. The red line is the continuation of the blue line from the previous page. Find the slope. The slope is defined as how much calorie bornage increases if the average pulse increases by 1. It tells us how steep the diagonal line is. We can find the slope by using the proportional difference of 2 points from the graph. If the average pulse is 80, the calorie bornage is 240. If the average pulse is 90, the calorie bornage is 260. We see that if the average pulse increases with 10, the calorie bornage increases by 20. So the slope is 20 divided by 10, which is equal to 2. Mathematically, slope is defined as the function of x2 minus function of x1 divided by x2 minus x1. So function of x2 is the second observation of calorie bornage, which is 260, and function x1 is the first observation of the calorie bornage, is 240. So this x2 is the second observation of average pulse, which is 90. First observation of average pulse equals 80. So we have slope equals 260 minus 240 divided by 90 minus 80. So 260 minus 240 is 20 divided by 10. So that is equal to 2. Be consistent to find the observations in the correct order. If not, the prediction will not be correct. Use Python to find the slope. This one. To calculate the slope, the following code. Def slope x1, y1, x2, y2, s equals y2 minus y1 divided by x2 minus x1. Return s. Print slope. Print slope 80 to 40, 90 to 60. So let's try to have the demo. Okay, so the slope. So let's try to change this to what you call this one. Let's change the code for the slope for, let's say this is 70. So if this is 70, so that is 20 divided by 1.0. Let's try. That is 1. Yeah, that's correct. That's 1. So that's the slope. How about if this is 65, guys? Does it have a slope? Maybe a 0.8. The slope is 0.8. Okay. So what's next? Next is we're going to find the intercept. The intercept is used to find the function's ability to predict calorie bornage. So the intercept is where the diagonal line crosses the y-axis if it were fully drawn. The intercept is the value of y when x is 0. Here we see that if average pulse x is 0, then the calorie bornage is 80. So the intercept is 80. Sometimes the intercept has a practical meaning, sometimes not. Does it make sense that the average pulse is 0? No, you would be dead and you certainly would not burn any calories. However, we need to include the intercept in order to complete the mathematical function's ability to predict calorie bornage correctly. Other examples where the intercept of a mathematical function can have a practical meaning. Predicting next year's revenue by using marketing expenditure. How much revenue we'll have the next year if marketing expenditure is zero. It is likely to assume that the company will still have some revenue even though if it does not spend on marketing. Another is fuel usage with speed. How much fuel do we use if speed is equal to 0 mph? A car that uses gasoline will still use fuel when it is idle. Okay, find the slope and intercept using Python. The int.polyfit function returns the slope and intercept. So if we proceed with the following code, we can both get the slope and intercept from function. So this is the code, guys. Import pandas as PD, import numpy as NP. Health data equals PD.read.csv. This is our data.csv. Header 0, separator equals comma. X equals health data average pulse. Y equals health data calorie bornage. Then we have that code slope intercept equals np.polyfit xy1. Then we print that slope intercept. So let's click try it yourself. So this is now the code, guys, and uh, we print now the values, the 2 and 80, um, the 2 and 80, guys, the same data, and the result is 2 and 80, an array. This is the slope, the 2.0, the 2 and 80 is the intercept. Okay, so let's proceed. Isolate the variables average pulse x and calorie bornage from health data. So we have that x and y value now. Call the np polyfit and the function. The last parameter of the function specifies the degree of function, which in this case is 1. Tip, linear functions, 1 degree function. In our example, the function is linear, which is the 1 degree. That means that all coefficients are in the power of 1. We have now calculated the slope 2 and the intercept 80. We can write the mathematical function as follows. So predict calorie bornage by using a mathematical function expression fx equals 2x plus 80. So we have the task now. We want to predict calorie bornage if average pulse is 135. Remember that the intercept is constant. A constant is a number that does not change. We can now substitute the input x with 135. So function 135 equals 2 times 135 plus 80, that's equals 350. If average pulse is 135, the calorie bornage is 350. Next is define the mathematical function in Python. Here is the same mathematical function but in Python. The function returns 2 times x plus 80, which with x as the input. Example, diff my function x return 2x plus 80. Print my function 135. So try to replace x with 140 and 150. Okay, next, plot a new graph in Python. Here we plot the same graph as earlier but formatted the axis a little bit. Max value of the y-axis is now 400 and for x-axis is 150. So we have this code, import matplotlib.pyplot as plt, health data.plot, x equals average pulse, y is the calorie bornage, and the kind of line is equal to line. Excuse me for a while, guys. That okay. So after that, this is the code. No, let's try to click this one, and this is our output for this particular program. No, uh, we have the minimum and the maximum. So our maximum y max is 400. That is why it's limit only to 400. And for the x max is only 150. As you can see here, there's a label of 140 here, but that's 150. Okay, you can explanation for that. Import the pyplot module of the math library. Data from average polls against calorie bornage. Find line tells us which type of plot we want. Here we want to have a straight line. Plt.ylem and plt.xlem tells us what value we want to access, start and stop on. Plt.show shows us the output. So I guess that's all, guys. Thank you very much for watching. And yeah, we have Green, you've been here. Thank you, guys. Bye, everyone.